So next thing we're going to talk about are complex numbers. So let's take a look at a problem I've got for us here. Right? So I've got x squared plus 4 equals 0, and let's graph it. So let's think of this as y equals x squared plus 4. So if you think back to our graph shifting that we did earlier in the mini unit, here I've got a parabola that's shifted up 4 units. So I should get a graph that looks something like this. Now, if you also think about what a solution represents graphically, right? A solution to an equation is the x-intercept of the equation. If you look, there's nowhere along this x-axis that my graph is going to intersect. So I shouldn't expect to get a real solution. So let's take a look at what happens if I go back and try now to solve that x squared plus 4 equals 0. So let's solve by taking square roots, right? Because I can't come up with two numbers that multiply together to give me positive 4 and add to 0. So square roots it is. So x squared equals negative 4. And if I take a square root of both sides, I have x equals plus or minus the square root of negative 4. This is a problem. Up until now, we've always been taught and told that we're not allowed to take a square root of a negative, because there are no two real numbers that multiply together to give us that negative value. Okay? Or I should say there is no real number that when I square it gives me that value. Okay? So here's where we're going to introduce what are called imaginary numbers. So I need a way to represent that square root of negative 4. Mathematically, I need a way to simplify it. So what we do is we introduce the imaginary unit, which is typically written as a lowercase script I. Right? It has the following properties, and these are the two basic properties on which everything else is built. So I equals the square root of negative 1. So fundamentally, this is going to allow us to simplify a square root where we have a negative value. Right? And also then, by definition, if I square both sides, I also have I squared equals negative 1. So I have a quantity that's being squared that gave me a negative result. Okay, so in terms of a real number understanding that you've seen up to this point, you should probably be scratching your head and saying, that doesn't make any sense. Okay? Well, it doesn't, because these are imaginary numbers. Okay? So an imaginary number is of the form, and I'm going to write this in the lowercase, so a plus bi, specifically where b cannot equal 0, right? And the reason b can't equal 0, if the b value here, the coefficient in front of the imaginary term were 0, then I would just have a real number left over, right? I would just have a as a real number. And complex numbers are of the form a plus bi, where a and b are any real numbers. Okay, so one other thing that also implies, if, let's say I have a complex number like 2 plus 3i, okay, this is an example of a complex number where my real component is 2 and my imaginary component is 3i. But I could also have a complex number like 3 plus 0i, which would simplify to simply 3. Well, 3 is a real number, isn't it? So what we actually have is that our real numbers that you've been working with all of your mathematical lives to this point are really a subset of complex numbers. All the numbers that we have are complex numbers. The real numbers specifically then are complex numbers where the imaginary component happens to be 0, and you're left with just the real number component. Okay, so let me come back up to this real quick. All right, so here I had x equals plus or minus the square root of negative 4. So if I wanted to simplify this, here I'd have x equals plus or minus the square root, and I would break this down into negative 1 times square root of negative 4. Right? The reason I'm doing that is so that I can simplify this. The square root of 4 is going to give me a 2, and the square root of the negative 1 is going to give me an I. So my solution here to this equation is x equals plus or minus 2i. Okay? So we're going to break that down very much the same way as if we had, say, square root of 8. We would break it down into perfect square factors. 4 and 2. I take the perfect square, and I get 2 square roots of 2 here, right? Same thing when we have an imaginary. If I had, say, the square root of negative 12, right? Now I'm going to break that down into a square root of negative 4 and a square root of 3. The 4 is going to come out as a 2. The negative is going to come out as an I. And here we get 2i square roots of 3. Okay, so we're going to follow all the same square root rules that we've used in the past. Just that negative is going to come out as an I, and once I pull out the I, the quantity left inside the radical becomes positive, all right? Because I've taken that negative factor outside, and this I signifies that there was a negative factor that existed. Okay, so let's look at a couple other things. Properties with imaginary numbers. So first things first, I can add and subtract imaginary numbers just like I do real numbers or algebraic terms. So the analogy that I always give, or the helpful hint, is to think like terms. Okay? So what I can do is I can add my real components together, and I can add my imaginary components together, just like if I had an algebraic expression, say I had 2 plus 3x plus 3 plus 5x, right? I would add the 2 and 3 and get 5, and I would add the 3x and the 5x because they were like terms, and I would get an 8x. Same thing's going to happen here. I'm going to add my real components together. 3 plus 2 is going to give me 5. Then my imaginary components, 5i minus 2i, is going to give me positive 3i. Okay. Same thing happens if I am subtracting imaginary numbers. So if I had something, let's do 1 plus 2i minus the imaginary number, let's do 3 minus 4i. Okay. I need to distribute this negative to both terms of my imaginary number. So what I'm going to end up with is 1 plus 2i minus 3 plus 4i. And now I can combine my like terms. Here we get negative 2 plus 6i. Okay, so when we're subtracting imaginary numbers, don't forget you're subtracting both the real and imaginary component of that negative imaginary number, and we're going to have to distribute a negative 1 to both terms. In terms of multiplying imaginary numbers, we're going to follow our exponent rules that we followed for multiplying like bases, right? So remember, if I had something like, x squared times x to the 5th, these were like bases, and what I did is I added those exponents, 2 plus 5, and got x to the 7th. The same thing's going to happen here, okay? When I'm multiplying two imaginary numbers together, I'm going to have to FOIL and distribute the first term to both terms in the other number, and then distribute the second term to the numbers in the other complex number. So when I FOIL here, 2 times 4 is going to give me 8. 2 times negative 2i is going to give me negative 4i. 3i times 4 is going to give me 12i. And 3i minus 2i is going to give me negative 6i squared. Now, I need to ask myself if I have any like terms, and I do. I have a negative 4i and a 12i. I can combine them, and we're going to get 8 plus 8i minus 6i squared. All right, so for right now, we're going to say that we're done with that, but I'll come back to the slide here in a couple of minutes. So the next thing I want to talk about is powers of I, right? So if we think about our exponent rules, anything to the 0 power always equals 1. I to the first simply equals I. I squared, by definition, equals negative 1. Now this is where I want to show you how we're coming up with some of this. And up top here, I cubed, I could rewrite as I squared times I to the first. I squared equals negative 1, so I get negative 1 times I, or I cubed equals the opposite of I. If I had say I to the 4th, I to the 4th, I could rewrite as I squared, couldn't I? I squared is negative 1, and negative 1 squared is positive 1. So I to the 4th is positive 1. If we had I to the 5th, I to the 5th would be I to the fourth times I. I to the fourth was 1, so 1 times I is simply I. And if you notice, we have a pattern starting. I to the sixth will be I to the fourth times I squared. I to the fourth is 1, I squared is -1, and I get -1. These are going to repeat. And I to the seventh is going to be simply -I. So if you can remember the 4 that we started with here, I to the 0 through I to the 0 through I to the third, you're going to know everything that you need for this. Okay? And the simplest way we can break this down, our larger powers of I into smaller, more manageable powers of I, is to divide whatever the power of I is by 4 and looking at the remainder. Okay? Essentially what happens is what I was doing here where I pulled out a 4, and whatever was left over is going to be the power of I that I have after I pull a certain number of I to the fourth out. Okay, I'm dividing out a certain number. So let's look at something like, let's do like I to the 13th. Okay, I to the 13th, I could break this down and say, well, it's going to be I to the 12th times I to the first, because I to the 12th is a power of 4, and all those powers of 4 simply equaled 1, right? I to the 12th would be I to the fourth to the third power times I to the first. Well, I to the fourth is 1, 1 cubed is 1, and I simply have I to the first. Or I could have said, well, I've got I to the 13th. 13 divided by 4. 4 is going to go into 13 3 times with a remainder of 1. The remainder is the only part that really matters, because the number of times it divides, right, is going to be right up here in the exponent. It's I to the fourth to the number of times it divides power. Okay, so you're just going to get 1 that many times over, right? So if we had something like I to the, I don't know, let's say 26th, right? 4 is going to go into 26 6 times with 2 left over. So we're going to have I squared equals -1. Right? So if I come back up to this last slide, right, just like when we have fractions, I need to rewrite any of my solutions, any fractions in reduced form. Right? I need to do the same thing when I'm dealing with powers of I. Okay? So here I've got a -6I squared. So what I need to do is I need to rewrite this by replacing that I squared with the -1 equivalent. So this is going to give me 8 plus 8I, and really plus 6. So now I can combine like terms. 8 plus 6 is going to give me 14 plus 8I. And now I have a completely simplified imaginary number for this particular operation. So the other place that this comes in handy, not just dealing with operations with imaginary numbers, but in terms of solving equations that don't have real solutions. It allows us to represent that solution just without the real number by using the complex or imaginary numbers. So if I have here 5x squared plus 200, okay, I'm going to solve this by taking square roots right now. So I'm going to subtract that 200 over. It's going to give me 5x squared equals -200. And if I divide both sides by 5, I'm going to have x squared equals -40. And I'm going to take a square root of both sides because now I have a squared term and a constant, right? So we're going to have x equals plus or minus the square root of -40. And now I want to try and simplify square root of -40. So the negative's there, I'm going to have an I, and I need perfect square factors of 40. So I'm going to have a perfect square factor of 4, so -4 times square root of 10. Square root of -4 is going to come out as a 2i, so we're going to have plus and minus 2i times square root of 10. Square root of 10 has no more perfect square factors, so we are done simplifying. We have a final answer. I don't know why it doesn't want to give me a box here. There we go. All right. Complex conjugates. in the event that we run into something where we have an imaginary number in my denominator, I need a way that I can cancel that imaginary number out of the denominator, just like when you rationalize denominators to get rid of a square root in a denominator. So if I have an imaginary number, and imaginary numbers are typically written with z. So if I had z equals a plus bi, then it has a conjugate, and that conjugate is z with a bar over it, a minus bi. And the only thing that changes is that sign in between the real and the imaginary number. Everything else stays the same. So here's what's really happening. If I have conjugates for any numbers a and b, a plus bi times a minus bi, and I multiply them. So if I FOIL this out, I'm going to get a squared minus abi plus abi and minus b squared I squared. The abi and negative abi are going to cancel one another out. They're like terms with opposite signs. The I squared here with the negative b squared is going to be negative 1. So I'm going to have a squared minus b squared times negative 1, or simply a squared plus b squared. So if you remember back earlier when we talked about factoring, we said that we had a difference of squares formula, which was a squared minus b squared equal to a plus b times a minus b. But we said that if we had a sum in the middle, that this only worked with a difference. So if it was an addition of squared values, a squared plus b squared, that this no longer worked. Well, here now we actually have a squared plus b squared equals a plus bi times a minus bi. So we do actually have a sum of squares number, but it involves, or formula, but it involves imaginary and complex numbers, which is why we didn't introduce it earlier. So how else do we use conjugates? Again, I said to not rationalize, but to clear an imaginary from my denominator. So here in my example, I have 5 divided by 2 minus 7i. I need to get rid of this I in my denominator. If I simply have a single term that's imaginary in my denominator, just multiply by I over I. But because here it is a sum or a difference, I must use the conjugate. So the conjugate of 2 minus 7i is going to be 2 plus 7i. So I'm going to multiply by 2 plus 7i over 2 plus 7i. It's a really fancy form of 1. So in my numerator, I'm going to distribute 5 times 2 is going to be 10, and 5 times 7i is going to be 35i. In my denominator, when I distribute, I'm going to have 4 plus 14i minus 14i and minus 49i squared. The 14i and the negative 14i cancel out, just like I showed you on the last slide. Right? So here I have 10 plus 35i divided by, and if I do a little simplification here, I have 4 minus 49 times negative 1. I'm going to replace the I squared, which is 4 plus 49, or 53. So 5 divided by 2 minus 7i is equivalent to 10 plus 35i, all divided by 53. And this 10 plus 35i over 53 doesn't break any rules for having imaginary values in my denominator. So when we're using the quadratic formula, we can run into the same thing where we have complex solutions, right? Before, if you got a negative, you just said, well, I don't really know what to do here before, or we intentionally made sure that you didn't run into any of those. So let's do one of the two examples here. So let's use the first one. So if I let a equal 3, my b value equals negative 10, and my c value equals 5. Remember our quadratic formula, x equals the opposite of b, plus or minus the square root of b squared minus 4ac, all divided by 2a. So when I substitute in, I'm going to have x equals the opposite of negative 10, plus or minus the square root of negative 10 squared minus 4 times 3 times 5, all divided by 2 times 3. So we're going to simplify. We're going to have 10 plus or minus the square root of 100 minus 60 divided by 6. So here we're going to get 10 plus or minus the square root of 40 divided by 6. So when I simplify, 40 is going to break down to 4 times 10. Square root of 4 is going to be 2. So we're going to have 10 plus or minus 2 square roots of 10 divided by 6. Now, I need to look and see if I can reduce my coefficients on the outside. Do they have a common factor? And in this case, they do, and it's 2. So I can divide everything by 2, and here we're going to get 5 plus or minus the square root of 10, all divided by 3. So this particular example actually came out to be real solutions. So I have 2 real solutions here. So let's go through, let's do the second one. All right, so A in this case is 3, B is 4, and C is 10. So here if I substitute, I'm going to have x equals the opposite of 4 plus or minus the square root of 4 squared minus 4 times A times C divided by 2a. So we're going to have negative 4 plus or minus the square root of 16 and minus 120 divided by 6. So I can simplify here. We're going to have negative 4 plus or minus the square root of negative 104 divided by 6. So we want to break down the square root of negative 104. So I know that 4 is going to be a factor, but I want to check to see if any larger perfect square factors would work, like 16 or maybe 36. Neither of them do. So if we divide 104 by 4, we get 26. So here we're going to have negative 4 plus or minus 2i square roots of 26 divided by 6. And again, if you notice, all 3 of my coefficients are divisible in this case again by 2. So I can reduce this and we're going to get negative 2 plus or minus I square roots of 26 all divided by 6. All right, so we're able to simplify and use the quadratic formula, but also still break it down when we get a negative inside of the square root. So that part inside the square root is, it tells us a lot about the equation. It tells us something about how many and what type of solutions we're going to have for a particular equation. That part is called the discriminant. Okay, so that's the b squared minus 4ac part underneath of my square root. So again, our quadratic formula, x equals negative b plus or minus square root of b squared minus 4ac, all divided by 2a. Again, it's quadratic formula. The way we use it, we identify a, b, and c, and then we substitute into that particular formula, right? And we simplify. Now, the discriminant is what I really want to talk about here, okay? The quadratic formula is nice because if something doesn't factor, we're still able to solve it with the quadratic formula. Doesn't mean it's always going to be nice. It could be pretty messy. And if something factors, that's the way we want to go because it's typically going to be simpler. There's less math involved and there's less chance you're going to make a mistake. All right. But again, the piece I want to talk about right now is the discriminant. I want to talk about the b squared minus 4ac part. So what it does is it tells us the number and type of solutions that we're going to have, right? Are they going to be real? Are they going to be imaginary? Am I going to have 0 solutions, 1 solution, 2 solution, or am I going to have 2 complex or imaginary solutions? Okay, so here I've got a nice little chart for us, right? So if my discriminant, and again, my b squared minus 4ac, so b squared minus 4ac equals 0, okay? Or sorry, if b squared minus 4ac is negative, let's start there. Then we're going to have 2 imaginary or complex solutions. So b squared minus 4ac is less than 0. I'm going to have 2 complex solutions. We write that as a C with a vertical bar, so a script C. If b squared minus 4ac equals 0, I'm going to have one real solution. Okay, it's going to be the same solution. It actually does occur twice, but it's the same solution that occurs 2 times. Therefore, it's only one distinct solution. And the second one, or the last part here, breaks down into 2 pieces. If b squared minus 4ac is greater than 0, okay? One, we're going to have 2 real solutions, but if it's greater than 0 and it is a perfect square, so like a 4, a 16, a 25, then we're going to have 2 real and rational solutions, right? Which also then would tell me that this was something that we could have factored, okay, that we missed a factor somewhere. If it's positive and it's not a perfect square, then what we're going to have is 2 real irrational solutions. So there's still 2 real, but now we're going to have a radical that stays. It doesn't cancel out. I can't break it down completely. Okay, so a little graphic of what we've got here. So again, if the discriminant's positive, I have 2 real solutions, right, or roots, and they're going to occur at these 2 points here where my graph crosses the x-axis. If my discriminant equals exactly 0, I have one solution, and it's actually going to be the vertex of my quadratic function, and it's going to be the point where the vertex touches the x-axis, right? And if I have a discriminant that's less than 0, notice that there are no places along my x-axis at which my graph is going to touch. Therefore, I have no real solutions to this particular equation. Okay. We're going to stop there. We'll do a couple of these in class, and we'll talk about that tomorrow.